let's say HCl, right? And then I turn that into Cl minus plus H plus if I put it in water. Remember when we looked at one type of acid and base, when you put this into water, what is this considered relative to that? It's conjugate base. This is an acid, this would be its conjugate, if it was in an equilibrium,
Yes.
right? This would be the conjugate base. So any anion, as it can be thought of as a conjugate base off an acid. That's essentially what I'm saying here. Okay. But that's not the interest. So that's great, that's obvious, even though it's never been stated that way. But what the interest is, then if I take this and I just put that into water, now what happens? That's my interest now. Does that change what's going to happen to the system? In this case, this is a single arrow. So single arrow means all of this turned into this. So I put that into water, what happens? Nothing. So that means this is a neutral solution. When I put that in, is it still neutral?
Yeah.
Yes.
Yeah.
And that's what we're going to discuss today. Those are the kinds of things we're discussing here. Okay, so, oh, they're using Cl minus. Okay, so Cl minus, I thought it was actually.
The next one is
this is the first one because this is a strong. So I'm looking at the conjugate base of an acid. In this case, the conjugate base of a strong acid. Okay. Here is the conjugate base of a weak acid, right? So if I put this one into water, what happens?
It's not going to dissociate.
I'm putting the conjugate base in.
Uh-huh.
So I'm now putting HF, I'm putting F minus in, plus H2O. That's not coming off of a strong acid.
Right.
That's coming off a weak acid, which means that what? When I look at the original formula here, what's going to happen? This goes like this, and I get H3O plus F minus. Is most of it on this side or this side?
This side.
This side.
Right.
So if I extract that out on its own and mix it with water, will it pull off one of those H's?
Yeah.
Absolutely. So what happens if it does that?
Makes it
Maybe I get something like this, and I get the HF plus the OH minus. What did I just make the solution?
Hydroxide base.
Basic. Absolutely. Everybody see that? And that's the concept here. The key is, what am I taking as the conjugate base off of the acid? And how is that affecting H2O on its own? Okay. So it's this. If I take the conjugate acid of NO3, I get HNO3. And of the acetate, I get acetic acid. Okay. So the anions can always be thought of as the conjugate base off of an acid if it was an acid to start with. But what if it's not an acid? That's even better, right? What if I had Na here, NaCl? I could just exclude the Na if I know the Na is what? If NaCl, what happens with NaCl when I put it in water?
Dissociates.
Dissociates completely, right?
Yeah.
Okay, what if I added, silver? What if I had silver chloride in water? Everybody remember what happens with that? Precipitate,
Yeah.
right? So then what happens if I have Cl minus coming off of silver chloride?
And that is make the solution basic, right?
Would it do anything? It's precipitating out.
Mm-hmm.
So would I have any free chloride or silver? What if I mixed NaF?
Oh, okay, nothing.
Why would it be any different than the HF? I still have the Na and the F will separate, which means I'll simply have the Na
okay,
can
all
do
of them are
something. Does the
ions.
Na do anything with water?
No.
No. But would the F do something with water?
Yes.
It would still do something with water, right?
Mhm.
That's the whole point. So it doesn't always have to be coming off of an acid is what I'm getting at here.
Okay.
Okay, and we'll explore that. I think we'll explore that a little bit. The key here is that what am I getting out of this piece? I should say the cation versus the anion in the solution. Okay, that's ultimately where I'm leading with this. I want to be able to separate and distinguish what each one will do when I mix it with water on its own to determine if it will have any overall reaction and affect the basicity or acidity of the solution. Okay, since we're in acids and bases, that's what our focus is here. So, blah, blah, blah. Okay. An anion that is the conjugate base of a weak acid, here, that's this here, will act as what? A base. Okay. An anion that is the conjugate base of a strong acid, and the example was HCl that I gave initially, will act as what? A base, an acid, or nothing? Nothing. And that nothing will define as pH neutral. Okay, so that's all that's saying. It doesn't act as a base or an acid. One way to define it is just simply pH neutral. It's just a term that means it didn't create an acid or a base within the solution because it didn't interact with the H2O. And that came off of a strong acid. Okay. That's because you had 100% completion, ionization, right? So it shows it doesn't interact with anything. Okay. Now, okay, so here's the fluorine. So here's what I did there, basically. If I take the conjugate base off of a weak acid, I mix it with water, I get this. And there you can see I get the hydroxide concentration. How would I know, or can I figure out with enough information what the actual pH would be in this solution? Yes. Is this an equilibrium?
Yeah.
Yeah.
So would I have a K something?
Yeah.
Right.
I'd have an equilibrium constant for sure, right? Also, if I had some concentrations, would I know?
All right.
Yes.
Ice chart.
If I had some concentrations, I could do a
Ice chart.
ice charting. So I can determine exactly how basic I can make this, because once I have the hydroxide concentration within this equilibrium, can I now solve for the pH?
All right.
Yes. Or the pOH if I want, right? Whatever I want to do. Okay. Okay. So if I look here, I could say, okay, why does this do this? It does it because if I look at its acid part, when that happens, I get this. I get this equilibrium, so I create this right here. This implies that this equilibrium here, would I prefer to be on the reactant side or the product side if I look at a K here? Is the K going to be high or low? Low, and that's because this is much higher. What do we use for K? Concentrations.
Right.
The concentrations of these are much higher than those. Which means that this prefers to bind that and form this. Hence, when I put this into water by itself, it's going to bind a hydrogen, leaving hydroxide. Right? That makes sense? So, everything I just said, what else we have here? And this is essentially what this is showing here. So this statement is represented by this equation right here. So, no big deal. Nothing that new, but what's different here? What's different is the first thing you could say is, well, how much of this do I have going this way? And then I could take this and I could treat it on its own. I could put it with sodium fluoride as well. And in that case, what would my equation look like if I did that? Sodium fluoride, and I wanted to see whether or not this is a base or an acid. Do I normally think of sodium fluoride as a base or an acid?
No.
No. Right? So that's why this is a little bit tricky. It's not a traditional way to think about it. If I said this, what would you say?
Yeah, it's an acid.
It's an acid. That's pretty obvious.
Right.
This isn't so obvious that it's a base, but it is. Why? Because if I do this, and I put this in water, I get the Na plus F minus. Then if I put the Na in water, what happens? Nothing.
Nothing, right?
But if I put the fluorine in water,
Gonna get
what
that.
happens?
Make that H.
So this is actually what? A base.
Gotcha.
That's the twist and the new component that you won't be used to and probably not comfortable with right away. So then how do you determine that? You determine that by knowing what the cation and the anion will do on their own
With water.
if they're separated in water. Absolutely. Okay. Go ahead, Raj.
But it won't be written out in two steps like that. You just, if it says aqueous, you should assume that they're dissociated of it. So you have to.
You can write it out.
You mean this says aqueous here?
HF, yeah, if it said aqueous, it wouldn't write out NA and F as separate.
I would write it like this, and then this would be aqueous, and this would be aqueous. And now what would I do? I would write each one and say, what does each one do?
Right.
And then one of them, the Na plus, isn't going to do anything on its own. I'm going to put that with water. Then I'm going to put this one with water. I'm going to say, oh, look at that. It actually does something, right? It creates a base. So this creates a basic solution if I put this into water,
Right.
which is not what I traditionally think because it doesn't come across as an acid or a base.
It's not
On
the
its own.
easy constant lottery. You can see it. Oh, okay.
Right? And then I could figure out what it actually is. If I do an ice chart, would I do the ice chart with this equation in water or this equation in water?
The second one.
The second one, because this isn't doing anything.
No.
It's having no effect on the basicity or anything else. I'm not forming any hydroxide or acid. What if what I put in here was an acid? This thing could create an acid, and this thing could create a base. How would I know which one I actually have?
Which one's a higher concentration?
Whichever one's stronger, I'm going to have whichever one gives me more H3O plus or more OH minus, right?
Okay.
So I'm going to compare those. How can I compare those?
Okay.
Kas. I can compare with Kas and Kb, which one's higher. I can compare with concentrations, right? Because you know that the Kw is 1 times 10 to the minus 14. So whichever one is higher than that or lower than that will tell me what I have.
Okay.
I'd have to know something though in order to make that determination. Whichever one gives me more of a base or more of an acid, more of a hydroxide or more of a H3O plus, would dictate whether or not that one was more acidic or basic. And I could do that by either getting the Kas or the Kbs or having them or solving ice charts or whatever else I need to do. Okay. 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 So that's this. So then if I look at a chart like this here, I have the acid and the conjugate base along this side here, and here's the acid. So I look at a strong acid, that's going to create a neutral solution, the conjugate base of that. Okay. But I get over here, right here, and I start moving down through here. I have all weak acids. This one's kind of in between. And as a result of that, that creates what I would call weak bases. And down here where I have something that's negligible or not really, very little if anything, then then I end up with strong bases. Okay. And I could look at it like this. Strongest acid is the weakest base. Weakest acid is the strongest base. And I just look at that chart and I go up, down accordingly. Now, so here, pH of a solution, acting as base, calculate, blah, blah, blah. We know how to do that. We call Kw equals Ka times Kb. And that allows me to make a determination of something. And we'll see what here. So I look at the anion, which is also the conjugate base off of a weak acid, right? And each anion listed below as a weak base or pH neutral is, what do I want to look at here? I want to look at the actual acid that this came from, and then I make a determination, is that strong or weak? Right? And if it's strong, what solution would this give me? A pH neutral solution. If it's weak, what would the solution give me? It would give me a basic solution. Right? So this is HNO3. I get to do all of that. This is HNO3. I was hoping it gave me this and then the last column. So is this strong or weak, and how do I figure that out if I'm not sure?
The O's on the H.
So it's
Two or more.
Two more oxygens than the acid hydrogens. So that makes this strong. So if this is strong, when I put this into solution, will it do to the solution?
So you can flip it.
pH neutral,
Right.
right? pH neutral. Is that okay? What about here? Let's now, this is HCO2. Is this strong or weak, and how do you determine it?
That's one.
That's weak?
Yeah.
Because it doesn't have 2 or more oxygens per hydrogen, and I should say acid hydrogen. This one doesn't count because this is connected to the carbon. So I have two of these, one of these, that's one more. That means it's a weak acid. If it's a weak acid, that means when I put this in water, what will it do? It's gonna make hydroxides. It's gonna act as a weak base, so therefore I make the solution basic. And lastly, what about this one?
That's 2 or more as well.
This has 3 oxygens more, so is it strong or weak? Strong. What is it gonna do to the solution? pH neutral. Is that okay? Does that make sense? Starting to, it's new. It's a different concept. Okay, good.
2 minus 1.
So, now the new question here. Calculate the pH of a 0.1 molar sodium CHO2 solution, and I give you the Ka for this.
Okay.
What I want you to recognize here are 2 things. I'm giving you the Ka for the base acting as its acid, because that's what a Ka is. It's based off of the acid, right? So even though this isn't given as HCHO2, if I just look at the conjugate base off of what this would be, I would end up with the CHO2 minus. So the sodium isn't doing anything in here. So what am I have this. Can I now figure out this?
Yeah. Using the ice chart.
So what am I doing here?
Make an ice chart and solve for K. Or
Make an ice
solve for
chart
K,
and
right?
solve for,
KW.
We'll solve for like the X using the K
okay?
to solve for the other concentration.
Everybody see why I'm pointing this out, the way I'm doing this? Think about what's happening here. What, okay, let me do this without just, you guys don't have the answer to this, right?
No.
Good, because I want you to think about it as opposed to just me putting it up and then you copy it. That doesn't do you as much good. Right? This is almost like you're studying at home because you're getting that insight now. You're working through the difficulties right through here. When I say Ka, what is that representing?
The acid, the equilibrium constant
That's what
of the acid,
and what
or
and what.
the product over the reactant of the acid,
So I gotta have what here?
product concentration. Doing it.
And
H.
NaCOH2.
what do I have? CH2O or something like that?
Yeah.
So
CHO2.
CHO2, and what would be here?
NaCHO2. Oh, CHO2.
So in reality, that end's not even there, right?
So the Ka it gave us is actually for HCHO2. Does that change anything?
Does what?
The Ka is for HCHO2, but
That's the
we
acid.
have the molarity of the NaCHO2.
Well, you need
That'd be
the
the acid.
similarity for the ice chart.
And in order to do this, I need an ice chart,
Yeah.
which means I always need what?
Equation.
Equations. What equations am I using here?
Right.
What am I doing here?
So you're
Put in
having the
CHO2
HCHO2 plus water?
Well,
Oh,
you
no.
know, if I just take the so I don't care about the sodium here. I take because the sodium's gonna give me pH neutral, it's not gonna do anything. So if I just take the CHO2,
And water?
CHO2, I could put the sodium there, but it's irrelevant, so I'm gonna leave it out.
Yeah.
I don't wanna deal with it because I don't want it to confuse me anymore. And I'm putting this in what?
Water?
Always in water, right? And then I'm forming some kind of equilibrium that's just gonna give me what?
Can you put the screen up?
Plus what? So what would I call, what is my equilibrium constant here? Isn't this K what?
KW? Oh, KB, yeah, right.
Is that KB?
Oh, yeah.
Yeah.
That's just the inverse.
Because it's making a base, creating the hydroxide.
It's just flipping this except for what's up here instead.
Hydronium.
Hydronium.
That's the acid.
That's the base part.
Right.
This changes from hydronium to what?
To the OH.
Hydroxide.
Right.
Becomes the OH. So this is essentially, this is now up here. This isn't a minus anymore, by the way. Fix that. and this is there, and this is down here, and that's up there, right?
Right.
If I have the K, can I solve the KW? Remember I just put up on the slide before, I said we'll get to that?
Yeah.
I could easily solve, what is KW?
KW is KA times KB.
Okay. So KW divided by KA gives me my KB, and I could use this, right?
Right.
Okay. You already see why I'm doing this. This is more than just, I gotta know what I have here, I gotta know why it's there, I gotta know what this is for me, and I gotta understand my equation, so I have my KB. Now if I plug in my concentration, I could do an ice chart. If I have KB, I can solve for what? What is it asking me for? The pH. So what am I trying to solve for here? I'm trying to solve for this.
And then you find the POH.
Well, I could then, once I have the concentration, can I then get the concentration of the hydronium ion?
Right.
And then I can get the pH from that, or alternatively, just like you said, I could then get the POH and take 14 minus that to get the pH. I could go either route once I get that, but the key here is what am I trying to solve for?
The OH.
That's once you have this, yeah, you could, then it's easy, right? Because you guys already know the quick conversion. I could make a POH, or I could make that into H3O plus concentration and get the pH. But if I don't know what I'm solving for, which is usually where the issue comes in, then I have, no idea what to do.
Mm-hmm.
How do I know what to do? The first thing is I had to identify what is showing me here and what this represents. Why do I have one, and how do I use them together? In other words, conceptually, I must know everything about what it is here. I can't just say, okay, if I learn this part and don't learn that, I'll get through. You have to know all of it in order to solve for it. But if you do enough problems, you should get comfortable. So let's see, step one, right? The balance equation for the reaction of the anion with water. That's what we did here. There we go. Okay. Then, what are we doing? Step two, set up and complete the ice chart from that. So that's just our minus x plus x plus x. We know we started with 0.10, and we're going to say approximately 0 here. Because why? You have the autoionization, so the little squiggly lines just mean approximation. Essentially 0. Don't need to worry about it, but just in case you're wondering what that meant. And then this is minus x plus x plus x. And now I set this up as what? X squared over 0.1. And I can get rid of that minus x because presumably it's going to be pretty small, so it won't matter, so I can cancel that out. The approximation method, I think we called it, or something like that, right? So I end up with x squared over 0.1 equals my k, not my ka. So some of you will make that mistake with ka, but this isn't ka because you're solving for a base.
Right.
So it's kb. So step 3, calculate the kb. We did that. That's pretty simple. Assuming you knew to do that, it's simple, right? Plugging in is pretty simple. Not knowing this is not always, knowing this or not knowing this is not so simple. You have to recognize that. Okay? Remember, kW is always 1.0 times 10 to the minus 14, just to keep that in context. Right there. Okay. Then, I can now solve for the hydroxide by plugging in my Kb in this whole thing. Approximation method, I get rid of that x, which makes that pretty easy. I take this times 0.1, square root it, and that gives me my hydroxide concentration. So this looks like a pretty intense problem, but if you understand it, it's actually not. But understanding it is not so easy, right? That's what we're doing now, is trying to work our way through and appreciate what's going on. Once you get here, just as Taylor said, I could do all kinds of things here, and let's go the POH route, which you mentioned. That's 5.63. So then the pH is 14 minus that.
Mm-hmm.
Okay. And that gives me 8.37. So there's a lot of steps here, which means that this is a nice problem, type of problem for the problem solving, right? Could take you, if you know how to do this, this isn't going to take you that long. If you don't, you're going to spend 15, 20, 30 minutes fumbling around with it, right? So this is the kind of problem where your worksheet isn't going to necessarily help you. If you have to rely on your worksheet to figure this out, you're wasting your time. This is something you should be able to look at. You have to evaluate it, which your sheet will not evaluate it for you. And then you have to be able to work through. So you have to understand what's happening intellectually so that you could set up what you're solving for and how to solve for it. Because once you do that, if you know how to do this problem, you look at it, spend a minute or two evaluating what it means, your strategy, to actually solve for it with your calculator shouldn't take you more than 5 minutes. If you don't know how to do this, like I said, this could take you the whole 2 hours just fumbling around with it, right? You keep going in and out, you're playing around, you're looking at your sheet, and somehow the sheet's gonna tell you how to do this, and it won't, right? So that's why be careful when you make the sheets. Write things that are useful, but you don't think that that's gonna solve, that it cannot solve this problem for you. Right? But then if you know how to do this, it's relatively simple, if you know how. It's not relatively simple to get to the point of solving it. But once you get to that point, then this problem becomes easy. Okay? Big difference. So sometimes you hear, I think that's the distinction a lot of times. I remember I was sitting in class and the professor would say, this is an easy problem. I don't think he meant literally that intellectually it was an easy problem, but once you understood it, it's an easy problem. But understanding it is the challenge. Okay? So keep those two things in mind, because once you get it, then you shouldn't have a problem. Just do what you know, right? Work through it logically. However, whatever, I'm not going to give you something that's outside the scope. You'll have different numbers, maybe a slightly different presentation, but it's the same thing. Okay. Katones, I guess they mean cations,
Cations, yeah.
as weak acids. So we just got done talking about anions, right, as weak bases. So cations can also be weak acids, right? And that's the same thing we talked about here with the sodium. That would be pH neutral. What would, let's take some and see what we have here. So cations, we'll call those counter ions of strong bases. Okay. Just a term, new term, nothing major there. Cations that are conjugate acids of weak bases. Okay. And cations that are small or highly charged metal ions. These are the three types of cations that can act as, potentially act as weak acids. Meaning that if I put the cation here with the water, it would form what?
Acid.
And that's the whole point. It would now form H3O plus, the same way as the anion off of a weak acid would form a base. Okay, that's all I'm looking at here. So let's start with number one, cations that are counterions of strong bases, such as sodium hydroxide or calcium hydroxide. What's going to happen with? First of all, let's make sure. Now hopefully your Chem 65 101 kick in, right? What is a cation and anion? Make sure we're clear on this, right? And here I'm looking at the sodium and the calcium, right? That's the whole point here. And I'm saying, well, what are those if I mix those individually with water?
They're gonna dissociate.
Just hang out.
They're going to hang out. They're not going to do anything,
Right.
right? So,
Oh,
my younger brother might say they'd be chilling. Right? They're just in the solution doing nothing, which means that what kind of solution are they creating? Neutral, pH neutral. They're not doing anything. Okay? And that's all they're talking about here.
oh,
Okay. So let's take, it's not going to show us an example. I think I did an example. I like to do these so that you can see how, when I think of a lot of this stuff, as you notice, I write up something like an equation and I equate what its concept is to that equation so I could see it, right? If I just read off of this, you guys can all do that, but it doesn't do a whole lot. If I just say, I'm just looking at the cation, so in this case it gave me sodium hydroxide. I'm not going to include the hydroxide, just have Na plus H2O. What does that do? Do I get an equilibrium?
oh, yeah.
No, I end up with just the H, I get just this, and I end up with H2O plus sodium plus.
Right.
Didn't do anything to the water, therefore it's pH neutral.
Gotcha.
That's all I'm saying. Okay? That's what this whole thing is saying. That's it. So in general, cations that are counterions of strong bases are pH neutral and form neither acid or basic. All of this is basically saying that, which is why I like to show this, because this is how I'm going to write it out to make sure I understand it. I don't necessarily need to memorize this. I just need to visualize what's happening, and then I can say, oh, that's pretty easy. Nothing's happening. Right? Okay. Second one, cations that are conjugate acids of weak bases. Okay, so now I have a weak base. So what would be a conjugate acid of a weak base? Give me a weak base. Let's start with that.
NH3?
NH3. Right, anything with amine. We looked at, what did we look at? The bigger structures that had nitrogens in them. What did we call those? Remember I went back and showed you that was actually on a slide earlier. Alkaloids, stuff like that. Okay, just to kind of keep memory jumping. So, okay, so this is a weak base. What is its conjugate acid? That's the conjugate acid,
Gain that
right?
H.
I just
Right.
added a hydrogen to it.
Right.
No big deal, right? And we've done these exercises before, just not in this context. So that's why this is how I think about it, which is exactly the progression that we've taught up to now. So now I say, okay, if I now take this and I put this into water, what happens?
Hydronium.
It is going to give off some, right?
Right.
And what is it going to form?
Hydronium.
Plus
and
an H3.
H3.
Right there. I just created what kind of solution?
Acidic.
Acidic. Right? See, now if I just read off, once again, just looking at the screen is not going to help you reading these things, but visualizing it, you could see, there it is. It comes right out at you. You can't miss it. If you write it out or think about it that way, you won't miss it. You'll know exactly. First of all, I need to know what a conjugate acid from a weak base is.
Right.
No big deal there, right? Add in the H+.
Right.
Okay, I might trick some people in Chem 101, but I'm not going to trick the Chem 102s. I don't want to trick anybody, but. So once I have that, then I'm simply saying, what am I always doing? I'm just mixing it with water. I'm creating an equation.
Right.
What does that give me? And this is literally what it gives me. It gives me this whole thing at some equilibrium, and that means I have some of this now, which means I formed an acid. So this isn't pH neutral anymore. This is now creating an acidic solution. So this is saying cations that are conjugate acids off weak bases are going to form acidic solutions. That's all I'm saying now. Okay, all the rest of this stuff is, going to be, could they do the same thing? They're doing it backwards here. They're giving you the conjugate acid off of the weak base. There's another one. And another one. So what's all in common? All I did was what? Add a hydrogen, and what did I form? A catone. Right?
What's a cation?
Which of course is a cation, to make sure that, I said that jokingly, but I don't want to confuse anyone.
It's like Googling it.
Right. Don't need to Google that, there should be an I there. Okay, so this is what's happening. These are the cations off of the weak bases. So that's okay. So I put this into water. I'm looking at each one of these into water, and what do I get?
Hydronium.
I get the hydronium. I create an acidic solution. That's all we're looking at here. Okay, so I could do something generic. Here's my base. That's the B plus the H plus. This is my cation. I mix that with water. I generically get the B on its own, and I get the hydronium ion.
Boron.
Okay, so that's what all of this is. So the pH of these kinds of solutions are going to be
Acidic.
acidic. And it's a pH calculation of a weak acid. Then you're basically just doing the same calculation you did before with ice charts and whatever else.
Doing it the other way. Getting the KB. Giving the KB then in this case.
Yeah, or if I give you the Ka, that's kind of even nicer, right?
A lot simpler.
It depends, yeah, a lot simpler,
Yeah.
right? Okay. Remember, Kw equals Ka times Kb, so if you have one, you can solve for the other.
Right.
But make sure you know which one you're using depending on what. Okay. Cations that are small, highly charged metal ions. I think we saw some solution that looked like aluminum with 6 H2Os. It was Al3 plus and 6 H2Os, right? So that would be Al, I think we had H2O 6 3 plus or something like that.
Yeah, that's the example.
Right? Is that the example? So that's something we looked at early on, right? Earlier. So if I look at something like this, and we're going to get into a lot of metal cations, by the way, and look at covalent bonding patterns and things, but we're not there yet. So this is something you've seen before. So if I put this is an anion, right? Or cation, I should say. And it's small, highly charged metal ion. Let me do something else here first. When I make this, I'm basically just putting aluminum 3 plus into H2O. H2O is just binding to it. And there before I just say it just dissolved. Now I'm saying it's chemically bound. Okay? That's kind of interesting. What did I do? I took it to a different level. Instead of just saying I just put this in and I still get Al3 plus, you know, and a lot of H2Os, I'm literally saying that in some format of this within the waters actually come and connect to it, and 6 of them will connect to it. So it's in some pattern, but 6 connected to this, what VSEPR structure would that be? You only know tetrahedral, which would be up to 4 bonds, right? Now I'm saying there's 6 bonds actually connected to it.
So hex.
So when we get to VSEPR, we're gonna look at higher level structures, and this is one. And why can aluminum do this? Maybe, would boron do this also? No, aluminum can do it because it has the, well, if I have 3 plus, so the instinct should say I have 3 plus, this should be what? 3. I'm saying there's 6, where'd the other 3 go? And why couldn't boron accept that? The orbitals. More Chem 101 all of a sudden, huh? Where'd that come from? So that's going to form a higher level structure, okay? And that you could look at like crystal field theories and other things that are much later on, but for now we could just think of things like an octahedral or something like that, and how the bonds are formed. And we'll get into, I think, as high as octahedral when we get into that section here in this class. But for now, I'm not saying that I'm taking this and this is dissolving. I'm saying that 6 of them are attaching in some structure to the aluminum, which also means that now I can take this itself and what happens when I add more water to it, which of course it's already in water, keep that in mind. But I'm now separating that out, okay? What could potentially happen to the water? And what actually happens is something more like this, H2O5 and OH minus plus what would be left?
H.
H3O plus. This is a cation. What is the cation going to do? Cation's going
I was gonna give away.
is going to form potentially an acidic or pH neutral solution, right? And
Oh.
anion is going to form a basic or pH neutral solution. This is a cation, small metal, and that's what essentially this is. Cations that are small, highly charged metal ions will form acids. This is kind of a trickier one, but I could also do it with iron at 3 plus, there's my aluminum 3 plus, etc. This is exactly how the aluminum 3 plus would do it. Okay. So, oh,
What do you mean
that is
by-
this example, here we go. So this is weird because this is balancing it out here, I guess. So you have the 6 here and the 6 there. Now I take this here and I put it into water, is that, okay, good. They take this, they put it into water, which remember, it's already in water, so this is all gonna happen at one time, not in these separate steps. Sort of like if you recall where we looked at redox reactions, and I broke it up into oxidation and reduction, half reactions, that those actually occur simultaneously. It was just a more clear way to visualize what's happening. Same thing here, this is happening at the same time. I'm just separating it out to illustrate what happens. And then you get this here, and here, there's actually a, you know, they left out the OH here, but there's an OH minus here because you only lost one hydrogen off one of the H2Os, right? So this becomes H2O plus, that H went on to here. This becomes this off of one of those H2Os, and then you're left with the OH minus on that. But that doesn't separate because you'll do that 2 or 3 times into the point where you get AlOH6. Right, and that becomes a negative, and then you end up with 6 of those. Right, and that's called aluminum hydroxide. But the key here is that what's happening here is that you end up with this small, highly charged metal ion. In this case, it's because it's binding to the H2Os, and then the H2Os are now readjusting to form an OH. So this should have an OH minus. I wonder why this should look
Yeah, I
like
was gonna
this.
ask you that.
It should look like this one here.
Okay.
on the notes.
The OH minus is there on the notes, not here. Okay, so this is there should be a hydroxide here. Just think of it like this, what I did here.
Okay.
And this, of course, isn't really a minus, right? Because that just stays there, and the overall charge of it is now gonna be what?
Okay.
2 plus, right? Does that have the 2 plus?
Yeah.
The 2 plus is right there, that's why it's 2 plus. Because you have 3 plus here, minus there, 2 plus total.
Okay.
Okay. So the key here, though, is, and a question, obviously I'm not gonna, we will get more into this, coordinated covalent bonding patterns and stuff like that later in a different chapter. But if you had a question, something like this, what you're really looking at is that a highly charged, small, highly charged metal cation can form, potentially, a weak acid solution. That's all. That's the only thing I'm holding you responsible for. I'm not expecting you to be able to put these together yet. We will, though, and I'll get more detailed in how to put these together.
When you
I
say-
give you some insight here, but I'm only worried that you know that. But you do need to put together the other ones for the equations that you're more familiar with. This you aren't as familiar with. That's why I walked you through it, and just to kind of like wet your feet in it a little bit. Like I said, we'll get more detailed into this later in a different chapter. Okay?
When you're talking about the small, you're talking about the electronegativity of it?
No, small size.
Oh, okay. You know-
Right.
Okay.
It's only on the third. So what would be a bigger one? Silver, gold would be much bigger.
Right.
Right.
Okay.
Okay, so now, we're gonna look at salt solutions and we're gonna determine whether or not they're acidic, basic, or neutral. And that's gonna close out this part of the chapter before we start and transition to a whole new area. Okay? Which is really just a combination of all the things we just talked about. So this is all different stuff. Let's look here. So I have, there are 4 different types of things, I think. They don't have the 4 here. Okay, let's look at the 4 different, you could write this down, 4 different types of salt solutions and how we interact with each one, if I recall. Should be 4. So I don't have a cation or an anion that could act as an acid or base. Okay? What kind of solution am I going to get out of that?
Neutral?
pH neutral. Okay. So I say here, I have counterions of a strong base, neutral. Also anions that are conjugate base of a strong acid. So either this, along with this, in my ionic compound, then I have a neutral solution or pH neutral. So all that, this is a little bit difficult to look at initially. The key here is that if I look at the anion and the cation, they're both coming off of strong acids and bases. As a result of that, they're pH neutral, because when I take either one independently and put it in water, nothing happens.
Mm-hmm.
That's what this is supposed to represent. I think this is really confusing. No matter whenever I've taught this and I put this up, everybody's like, huh? Even I have to look it over, the first couple times when I taught this 10 years ago, and I was like, what is this kind of saying? Right, because it's not a traditional chart. What you really, if you're going through your notes and you don't want to just listen to what I just said, this is the cation side, this is the anion side, breaking it down. This here is the counterion of a strong base, the cation, and the conjugate base of a strong acid. So these are just coming, the ionic compound is just coming off of a strong acid and a strong base. So when I mix each one in water, nothing happens. That's all it's saying. That's what all of that stuff is here. Okay? So these solutions are neutral, things like sodium chloride, calcium nitrate, potassium bromide. Right? Traditional stuff that you would expect. Okay. Second one. Cations that act as neutral, and anions that act as a base. So that means a cation came off of what? A strong base, right? So that's this one. Okay. But the anion came off of what?
Acid.
Conjugate base of a weak acid. So when I mix this with this, what do I get? Basic, right? But then if I don't even look at this, I already know that because I'm looking at the anion that's coming off of the weak acid. It's got to act as a base, right? If I just look at each one independently, so I'm going to look at sodium fluoride. Sodium's coming off of a strong.
Acid.
Coming off of a strong
Oh, base.
base. The fluorine is coming off of a
Strong acid, right? The
weak acid. See all this conjugate, strong base off of, or weak acid. This is coming off of a weak acid, this is coming off of a strong base. That means that this here, when I put that one into this equation with H2O, I'm gonna get hydroxide.
Right.
When I mix this one with H2O, I'm gonna get nothing. So if I get nothing here, I'm not worried about it. If I get a base off this, I'm gonna get a basic solution, and that's all I'm saying. Same thing here. Calcium I put in, nothing. I put in the acetate, it's coming off of the weak acid. That's gonna take some of the H's from the H2Os and it's gonna form hydroxide. It's gonna form a basic solution, same with the NO2. And how would I know that? So for example, how would I automatically know, because this is new, you haven't really seen this. You've seen it, but it's not something we've talked about a lot. I'm looking at NO2 minus, and I'm looking at potassium. Okay? If I make this into a base, right? So this is a plus, that's a minus. I get KOH. Okay? If I put this in water, do I get 100% ionization? Yes. This is a strong base. You know that, right?
All right.
It's not, it doesn't have a nitrogen, and it's not an amine group or anything else. It's a hydroxide. Okay. If I put this one as an acid, so I add an H there, HNO2, is this a strong or weak acid? 2 oxygens, 1 hydrogen.
Yeah, one difference.
It's what? Weak. So even if I didn't automatically know that, you could figure this out, which is why I keep showing you these things.
And then with,
This is coming off a weak acid, which means that now if I put this here in with water, I'm now going to form the HNO2 plus the OH minus. That's my base. That's how I know it forms a basic solution. So I break up each one and say, what does it do? If I'm not sure, I put it to its conjugate. And I say, what happens? Then I could evaluate. Here on its own, do I know that's coming off of, that's gonna do this?
No.
Maybe not. When I say, oh, it's coming off of that as an acid, is that a strong or weak acid? Well, 1 oxygen more than the hydrogen, that's gotta be weak. That means that when I mix it with water, I'm going to get this,
You can work on with that one. Okay.
right? So it's a progression of things that you have to think about, but if you think about it appropriately, you could break down what this is, one that you might not automatically know and quickly identify, you get a basic solution. Is that okay? Everybody see that? So the challenge is making sure that you put it all proper. So of course, what's the next one? The cation acts as an acid, and the anion acts as neutral, right? That would be the next one. Okay. Anion acts neutral, cation acts as that. So this is odd, okay. When you're going through the notes, I hate this when I see something like this. We just got done saying cation here and then anion, and the next one, now we flip it to anion. It should just stay consistent. You see where that becomes confusing. So don't get caught when you're reviewing your notes. This should really say the way, exactly how I said it, right?
Cation.
I said the cation is an acid, the anion acts neutral, and that's because I just got done saying cation here first and anion there first. They flip it only because it's the one that's actually doing something. But I think that adds to confusion because it's flipping things around, so you're not seeing them, in some natural progression, you're seeing them jump around. So when you're doing it on your notes, you might want to switch that. That'd probably make it easier.
Actually, the notes have it, the cation first.
It does?
Uh-huh.
Oh, good, okay. That's much better. So here, I have, so once again, these are going to be acidic. So what am I looking at? Let's just take a look at some of them. I have iron chloride, aluminum nitrate, and ammonium bromide. Anion, or cation. These anions are doing nothing, right? If I put them with H's, HCl, strong acid, doesn't do anything. HNO3, HBr, all strong acids. But if I mix the iron here with hydroxide or something, then it's a small metal one, the aluminum, and then the ammonium on its own, right? The NH3, so I'm looking at the conjugate of that, the NH3 is going to be a weak base. So I know if I put these things into solution, small, highly charged metal ion, or weak base, I form what?
Acidic solution.
Acidic solutions. And that's what you would see here. Small, highly charged metal ion and conjugate acid of the weak base. Okay. What's the last one gonna be? They both do something, right? The cation is gonna act as a base, and the anion will act as a? Mhm. So when I have that, cation acts as acid, anion acts as base. It depends on the relative strengths of the acid and the base. Okay. So examples, I now have FeF3, aluminum acetate, ammonium nitrite, right? So NO3 is nitrate. I drop one O, I get ite. I change the A to I for the nomenclature, so that's nitrite. So it depends on the, so each one. Oops. So how would I determine which one? What can I use to determine that?
Okay.
Ks, right?
Mm-hmm.
Ka versus Kb. If I have one, I could figure out the other.
Right.
Concentrations, higher than, larger than 1.0 times 10 to the minus 7, then it would be that one. Whatever's less, it wouldn't be that one in terms of what the overall solution pH would be. Okay, let's do, oh, here we go. So this is continuing the same one. pH depends, relative strengths, and you can compare Kas and Kbs. So if it's neutral, obviously those are pretty close. If it's acidic, the Ka is much larger than Kb, and if it's basic, the Kb is much larger than the Ka. So that would be one way to identify, and probably a pretty good multiple choice question. Okay, so going back through this, before we do a couple examples, what's the key to all this? Knowing what each ion does, right? And if you're not sure, how do you determine it?
Equation.
Look at its conjugate.
Right. Heavy water.
If you're not sure, look at the conjugate. And then from the conjugate, make a determination on whether or not you have a strong acid, strong base, weak base, and then how to identify. If I gave you something in a multiple choice question that had Ka and Kb, you could quickly assume it's probably similar to number 4, right? So there are some keys that you'll be able to figure out without wasting too much time in evaluating the question, right? If it gives you something, if you're not sure, especially if I gave you something and you're trying to figure out if I break this up into ions, is this ion going to be, off of a weak acid or a weak base or whatever else? And then I give you both the Ka and the Kb. You could probably assume you're looking at number 4, where both of them are doing something. Which one's doing more?
Just
Right?
compare them, right?
Just to keep that in. If you understand that, you'll figure that out. Okay, let's do some quick examples before we get into the last section here. For each of the following salts, indicate whether an aqueous solution. Okay, so I guess we're not going to actually do that because it already shows you. So this is, I'm looking at strontium. They're saying that's a pH neutral cation, and this is a pH neutral anion. Therefore, the solution is neutral. What did I do? I had to identify what this is and this is. And how do I know strontium is pH neutral cation? Just out of curiosity. Basically, it's in group what? 2. So anything in group 1 or 2 are pretty much pH neutral. Okay. They're not small, highly charged metals. pH neutral anion, Cl2, right? You already know what that. So if I took Cl2 and I added a hydrogen to it, I have HCl. It comes off of a strong acid. Okay, that's all. So we're identifying here. So there's no reason to read this because they're already telling you everything here. It's not like we're guessing. Be nice if they tested that, right? Which of the following salts indicate whether or not it's aqueous solution or acidic, and they give you this. And your answer is just circling it. Okay, aluminum, acidic cation, small metal, highly charged, and the bromium comes off of a HBr is strong acid, so that means that this is neutral, so it will be an acidic solution.
For the cations, is anything in group 1 and 2 would be basically neutral. For the anions, how can you
Go off of us whether or not, what is its conjugate acid? Is HBr strong or weak?
Right.
Strong. HBr is strong, right? The only
Right, Br.
binary acid that's weak that you have was HF, right?
Mm-hmm.
Everything else. So HCl, HBr, HI, those are all
HI, right.
those are all strong. And then of course if it's an oxyacid,
Mm-hmm.
2 or more oxygens.
Okay.
Okay, so acidic cation here, because if I add that to it, I have the NH group, so I know that's coming off of a weak base. And then here, this is pH neutral, NO3, which you know if you put an H in front of the NO3, you have 2 oxygens more than the hydrogen. So again, I'm just evaluating each one separately, because they won't be color-coded and they won't give you that information. Right? And so therefore, this is an acidic solution. How do I know this is coming off of a weak base?
Conjugate
Because if what's the conjugate of this?
is the CH3.
This is CH3, NH3 plus, right?
All right.
What's the conjugate of it?
The OH.
This has an N group. If you're not sure,
Or no, 3.
what did we say about N groups? Are they coming? Do they create weak or strong bases? Weak bases.
Oh. Yeah. The alkaloids. Yeah.
Right? That's how I'm determining these things, right?
Mhm.
So this is the NH is right there.
All right.
There you go.
That's
So you
right.
know that that's going to create an acidic solution. And you know the NO3 because I put an H in front of that, and then that comes off of a strong acid.
Mhm.
2 oxygens more than the hydrogen. Okay, so then this is going to be pH neutral, that's going to be acidic. And that's what I'm doing with each one of these. I'm just simply looking at what these are. Sodium mixed with OH, strong base, neutral. CHO2, if I put an H there, is that a strong or weak acid?
Weak.
Weak. 1 oxygen more than the hydrogen I'd put there, that's weak, that creates a basic anion. I'm separating them and I'm saying, what is the conjugate and what does it do? That's how I'm determining strong or weak depending on each. Okay. Let's do one more, make sure that before you, so this is coming off of a
Okay, that's a weak.
weak base, this is coming off of a
Strong.
weak acid, so I have an acidic anion and a basic anion, and I want to know
Yeah.
what the overall solution here is. What do I have to know?
Which one is greater, your case?
K's. If I know the K's, then I can determine it. So I'm assuming the Ka is greater than the Kb here. That's
Right.
why it says the acidic. So here we go. Ka is this, Kb is that. Which one's greater?
Okay.
Minus 10 is greater than minus 11.
Right.
Don't get confused by the higher number. They're negative. Therefore, I have an acidic solution.
All right.
Okay, so you'll have to do some practice. Oh, wait, what do we have here? Okay, let's walk you through this. This is kind of similar to what we looked at before, right? Household bleach is a 5% solution of sodium hypochlorite. That's NaClO. This corresponds to a molar concentration, about 0.7 molar sodium chloride, hypochlorite. What is the pH of the household bleach? And I give you the Ka.
Okay.
For HC.
Let's just walk through what we need to do intellectually here. What do we need to do? What are we trying to accomplish here? I want to know the pH. If I want to know the pH, what do I need to know here?
Your KB, Ka.
The concentration of hydrogen ion or the.
I need the, I ultimately want to know the hydronium or the hydroxide concentration,
Right.
because from one I can find the other.
Mm-hmm. Using the
That
line.
you should know right away. Okay, so then how do I get to that? I'm starting with this and I'm given this.
Yeah.
Mm-hmm.
This, if you remember, translates to starting with this. But I'm not starting with that, I'm starting with this.
Yeah.
So, the very first thing I want to do is I want to see what that means. I have 8 NaClO, right?
Oh, yeah.
Now, Na plus ClO minus.
Mm-hmm.
What's the conjugate of the Na? The conjugate base of this.
Yeah. NaOH,
Is that strong or weak?
strong.
Strong. So this isn't going to do anything.
Yeah, it's
Right.
Let's just get rid of it then. It's irrelevant. Okay. What about this?
H
If I add an H, is this strong or weak?
is strong. Weak.
1 O, 1 H?
Weak. One.
It's weak. Perfect. Let's keep that. That's going to do something when I mix it with water.
Mm-hmm.
Okay. So let's see what it does. If I'm not sure and I don't remember, what can that possibly do?
A base,
Yeah.
OH.
What did I form?
Base.
Base. Okay, I now know what I'm solving for here. I'm solving for the hydroxide based on this. Hence the importance of understanding the equation you're using and why. Started you guys off very early talking about knowing your equation when it was obvious what the equation was, because now it's not so obvious. You're figuring it out depending on what you're starting with.
Right.
So if I have a base here, what is the KB for this? What is the equilibrium for this? Obviously KB. Why is that important? Because what did it give me?
Ka.
Can I solve for the KB?
Yes.
KW over
K.
KA.
Okay.
So let's assume I have the KB. Now, I also have the concentrations of what?
Of the NaCl.
This one.
Yeah.
Yeah.
0.70, 0, 0, minus X, plus X, plus X. What is my KB is going to equal X squared over 0.70.
Yeah. And the
Okay.
other X is not-
No big deal. KB times 0.70,
Square root
easier,
X.
equals X squared, and then the square root equals X, and X equals the concentration of hydroxide. From here, I could decide what I want to do, POH, or solve for the hydronium ion and get the pH. Either way, I end up with the pH. Okay? Once again, not so hard if you understand what we're doing here. You don't even necessarily need to write this out. It's pretty obvious at this point, right?
Yeah.
X squared over 0.7.
You use the negative log of the concentration. Okay.
It's better to write out, right? Because if you do make some mistakes and I don't see this written out, then I'm kind of like, okay, they just didn't know what they were doing. Not that they knew what they were doing and made a calculator mistake, right? So if you do write it out, then that shows me you understood what was going on. You made one minor mistake here, and I could only take off a point or something. So keep that in mind. Okay, with that being said, let me quickly walk through that. See here, what they did, they took both and saw that there's no reaction here, but there's a reaction here. Or they took this and they broke it up, and they took this one, saw no reaction, then they take this one, and they see there's a reaction, there's a hydroxide. They need the KB, you got the Ka, they solve for the KB here, just like we did. Then we fill out this chart, that's gonna be insignificant.
The OH is 14 minus the pH, or the other way around.
Say that again?
The OH, I mean the POH is the 14 minus the pH. Right? Okay.
Okay, so then this is small, blah, 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 we get this, no big deal, this is just this times this, so the square root gives me this. Then I get the POH in this case, 0.3.35, 14 minus that gives me the pH. So the pH is 10.6, so in case you're not sure of this, write this number down and try to get it, and if you can't, send me an email, and I'll help you solve it. Just tell me what you've done up to this point and where you got stuck, and then I can help you get through that sticking point, okay? Another thing I should point out, over the break, you're gonna be studying, obviously, and if you come across something and you need some advice, send me an email. Okay, I'll respond, even
Awesome.
during the break. So keep that in mind. If you have problems and you want to, easiest way to do it nowadays, take a picture and send it on the email. Some of you do that, and then I can evaluate it, and I'll take my time and write the whole thing out for you. But you would just have to take a picture and tell me where you're stuck. But make sure you tell me you made some effort,
Right.
right? Just, how do you do this problem is not a good way to ask me. Especially if I want to take my time to solve it. But if you say, hey, I got to this point, I'm not really sure what to do here, then I could work you through that.
Okay.
So is the Ka here really needed to calculate anything unless you're gonna calculate KW?
Say that again?
The Ka that they give you here, in example 2, do we even really need it?
How else can you get KB?
25.
Oh, okay, so you're gonna,
You have to use the K to get, otherwise you don't have KB. But if they gave you KB, yeah, you don't need KA. Yeah.
because I was confused over there when you're solving.
Here,
Yeah.
this is the equation. Knowing that, you get a base.
Right.
That means you need KB. That's the first thing. So then if you know that, then you just say, okay, if I have the K, KW over K gives me my KB. KW never changes. So KW is always this. I gave you KA, But you need Kb because Ka would go for this equation, Kb goes for this equation. So I need the Kb since I'm solving for something with hydroxide. So I need Kb, I have Ka, I always know Kw, I solve for my Kb, now I could use my equilibrium constant. Okay. Okay, now, this is the I was hoping we'd get through this. Okay. From here on out, we're just going to talk about things that cause strengths for the acids and the bases and things. What causes something to be stronger or weaker than something else? And how to distinguish that. Okay? So, in other words, the strength of an acid depends on how easy you can get rid of the proton
Or dipole moment.
within a binary acid. That's the H plus. How easy that, so HCl, 100% ionization, right? That means it's strong. Why is it 100% ionization versus something that's a weak acid, right? Like HF. The change in electron negativity between that bond is going to be one of the factors. But also if I'm looking at an oxo acid, I'm looking at the strength. If I pull one off, what happens to how tightly it holds the rest of it together?
Or even tighter.
And how does it distribute that electron density once you have that, something like this? So,
Listen.
Thanks.
Yeah, you're welcome. I'll give $5.
if I take something like, let's say this is acidic acid, right? Or I should say,
S. Or
I
SO.
don't know if there's a C here, that's what I'm. This is my acidic acid. These aren't because these are too tightly bound here. If I pull this off, what happens here? Maybe I should put these here too.
Electrons. Don't pair.
Right? I pull that off, it goes as a proton, this whole thing becomes a negative charge. These electrons here now, there's too much electron density around that oxygen. They want to, what? They want that density to be able to
Sure.
delocalize. They're all localized here. I want it to be able to move through here, maybe move through there, and back and forth. I want to delocalize it. The easier, more delocalized I can make it, the more stable it becomes. Delocalize, where did that term come from? Chem 101 again. Ooh.
That resonance.
Resonance, absolutely. So if I can create resonance structures out of this, what did that do? Stabilized it, right?
Right.
Stabilize this thing. So if, depending on what if I only had that there? Can it delocalize through here the same way that oxygen?
Yeah.
No.
Oh.
So then which one would be more stable?
Yeah.
In other words, which one would be easier to pull off the H because of the stability after pulling it off versus which one would be harder to pull off because afterwards it's really unstable. I can't. And that's the strength component that I'm going to discuss now. In terms of, is it a strong or weak acid? It's a stronger acid if I could delocalize the area of electron density. It's a weaker acid if I pull that off, and I can't because it's now harder to take off because what I have left is less stable. And that's the foundation for this, the rest of this chapter.
Gotcha.
Okay, that's the key to it. Okay, so the ease of the proton coming off, you look at the polarity of the HY bond, that's only when it's HY, and the strength of the HY bond. So the key there is understanding what is Y here. Right? So here Y is C, but then also what's surrounding that, what's connected to the Y. Okay. Okay, so to be acidic, you have the HY here, you have a partial positive on the hydrogen and a partial negative on whatever this Y is, and the greater that distinction is, or the greater the change in electron negativity, the easier it is to pull that off because the more positive this is and the more negative that already is on its own. So therefore separating it should be easy. Now here, if you look here, everybody remember what a dipole moment is? Do I need to
Yeah.
refresh? No, I see some people shaking their heads. This is real quickly.
For the electron.
Let me see, let me do this. Everybody mind staying an extra 5 minutes?
No.
Is that okay?
Yeah.
Okay, because we started late, and this way you'll have a better sense of what to look at during the break, as opposed to just doing it on Tuesday and then taking a test on a Thursday. I give you a little bit more feedback, and then we can, okay, let's do that. So here, I have, when I have the H and the Li, I wanted to do this real quick. H2O, that's a partial positive, partial negative, partial positive, partial negative, meaning a dipole moment. If I go right down the middle of the molecule, this is my negative side. I cross my positive side at any given time. This is my dipole moment. Part of it's positive, part of it's negative. Okay, that's a dipole moment. So the larger the dipole moment, the easier it is to pull something off,
Because all the electrons are.
because all the electrons are already there.
Mhm.
Okay. So here, if you remember the rules in defining oxidation states or numbers, right? That was a pseudo scheme to determine the redox reaction on one side if you had how many electrons and then how many you had on the product side, and if you had a loss or gain of them,
Right.
right? So that was using the oxidation number. So if I had hydrogen connected to
Lithium.
a metal, then the metal is going to be more positive. The hydrogen becomes negative. If the hydrogen is connected to a C, they're kind of neutral. That's why it's hard to pull off, because the electrons are almost equally being shared here. But if I have a more traditional sense where I have the H and the F, this is more positive over here. This is more negative over here. So this is going to be the easiest one to pull off, even though this one's not going to be that easy to even form, right? So if I did form it though, this would be acidic, presumably, because if I look at the H come off there, this one, not going to do anything. And this one, if it's connected, is really not going to do a whole lot. Okay? It's got a backwards dipole moment, essentially, there. Okay. Here's for the strength. The higher the electron negativity of Y, the greater the change in electron negativity, okay? The more polar the bond, the easier it is to come off, referring to the proton. Nothing new there. That's exactly what we learned when we learned polarity in Chem 101. And the easier this comes off, the stronger the acid. That's a very simple concept. Nothing new to what you already know. Okay. So now, the strength of the HY bond, once again, you're going to remember this from the periodic properties section in Chem 101. If I have something this small, my hydrogen's over here, the center here is my nucleus, versus something here, the hydrogen here in the nucleus, which one's easier to pull off, this one or this one? The one further apart, right? Because it's not being held as tightly.
Right.
So the larger the Y, the weaker the HY bond, right? The less tightly the H is held, the easier it comes off, the stronger the acid. Once again, nothing really that new there in terms of conceptually. That's all what we learned in Chem 101. Okay. So now, looking at trends, and once again, this is pretty basic. Electron negativity of Y increases, polarity of HY increases. I'm looking at diagonally also, so also going up, the same thing as going left to right. Okay, so H2O is weaker than HF, and that's in terms of an acid. No big deal here. I'm going to move through this pretty quickly. S is weaker than HCl, and that's because S is here, HCl is there, so going to the right, it gets stronger. Going up, it gets stronger, with the exception of fluorine. And I think we talked about fluorine and its ability to bind to itself. Right? Okay. Down a group, same thing. So now, well, here the strength gets weaker as I go down in terms of the electron negativity, but in terms of the strength, it's going to become easier to pull off the H because you get a bigger Y, right? Y gets bigger, easier to pull off the Y. So here I have HF, HCl, HBr. Bond energy is this versus this versus this. Type of acid, weak, strong, strong. What they're claiming here is that the weakness of, or the closeness of the HF bond here is greater than the difference in electron negativity, creating a weakness for this one, and these are stronger. Okay, so the atomic size increases, and the strength of the acid increases, the bond strength decreases. Okay, so bond strength decreases, acid strength increases. Just because of the size, no big deal. Okay. And here's a diagram kind of illustrating that. So when you look at this, you have the decreasing bond strength, which means it's increasing the strength of the acid. So you start here, the darker color means that it's more acidic. So here is weakly acidic. This is a little stronger acidic, weak acidic, stronger, stronger, stronger. These two are about the same acidity, and this one is a little less than these three. Okay. And that's because of the dynamics between the size and the electron negativity. What's that?
No,
Oh.
blessing someone.
Okay, so oxoacids are these, and this is now where a lot of the questions on multiple choice will come from and how these patterns work.
Oh.
Okay, because now I'm going to add more, because now I'm looking at the hydrogen here, just like here, connected to the oxygen, connected to the Y, but the Y is also connected to other things. These other things it's connected to is what's going to dictate how strong or weak, or how strong of a weak acid you have here. Okay. So the general polarity of this determines the strength of the acid. That's the bond here at some level. Okay. That's the electron negativity. And then now, here's another twist. The number of oxygen atoms bound to the Y here. Not just this one, because you always have this one when you're dealing with an oxoacid. But do I have any more oxygens connected to this Y? The more oxygens I have connected to this Y, the stronger the acid is, the more weakly bound it is. Because when it comes off, the more oxygens help delocalize the electron density on this oxygen.
Mm-hmm.
So the more oxygens I have connected to Y will increase the strength of the acid by decreasing the dependence of this hydrogen to that oxygen. Okay?
Mm-hmm.
So I see here, this just if I look just these things here are the electron negativity patterns, and you could see the Ka's do what? They get larger coming down here based on the increase in electron negativity when
Okay,
the
going
only
up,
thing
right.
connected to the Y
Yeah.
are these. Okay? Which means that the polarity plays a role, right?
Mm.
This is the most polar, therefore the greatest change in electron negativity. This is Y, by the way. This is representing Y. And therefore the highest Ka, meaning the most on the product side, meaning a stronger acid.
You said the O is the Y?
No, the Y is this here,
Gotcha.
right?
And then it's connected to the acid. Okay.
So that's how the electron negativity plays a role, okay? The more electron negative the Y, the IBrCl in this case, the more polar the HO bond, and therefore the easier the H plus is lost, the stronger the acid. That's all it's saying. Okay. Now, here, this is just a repeat of that. Okay. That's exactly the same. So two slides that are identical, pretty much. Okay. Now, this is the new, that should be obvious. But that also, if you saw, only slightly increases the Ka. This is where you might not be as familiar with. The more oxygen atoms that are connected to the Y, other than the oxygen holding the hydrogen, that increases the strength of that acid because it decreases the dependence of the hydrogen to that oxygen, because you can now have the dispersion of the electron density around more oxygens relative to the Y, and therefore reduce the location or the localization of the electron density. So here, this is a strong acid, and you see why. By the way, this is the first time you're going to see that correlation between number of oxygens to acid hydrogens. This is why I'm able to say that. I never explained it because we never got there. The more oxygens relative to the hydrogen, the acid hydrogen, the greater or the more easily I could delocalize the electron density from that hydrogen. Once I release it, therefore it makes it stronger. Here's an example. HClO4, 3 oxygens to 1. So I pull this hydrogen off, I now have a charge here that can be delocalized all over the place on that molecule. So pulling this off is not that big of a deal to what's left because the electron density isn't stuck in one place.
Right.
Hence,
Stays
this
stable.
becomes a stronger acid and easier to pull off that hydrogen. Over here, I have 3 of them. So here's my Ka, strong, obviously. Strong meaning what? There's no number there. There's no Ka, it's strong.
Right.
This one here is 1, 2 more, 1, that's pretty much like the same thing. Over here though, I now have only one air, so now, here if I pull this off, I have extra density that can be delocalized this way and this way.
Yeah.
Here it can be delocalized 3 ways, here it can be only delocalized 1, and now it's a weak acid, and I have an actual Ka for it. And the same thing here, now there is none, and look at the jump between the lack of delocalization versus delocalization once I pull the H off. That's a huge difference in Ka.
That's a weaker.
This is a much weaker acid as a result. This is a much stronger acid of those weak acids, and these are obviously strong acids. Hence, 2 or more oxygens
per hydrogen.
per hydrogen. Press. Now you get a chance to see that's because of the delocalization of the electron density, where before, if I don't have the delocalization, now it's all stuck here. That's a really unstable molecule. All the electrons are sitting around there because remember, both electrons go here. This comes off as a proton.
Yeah.
Okay, and that's the rationale there.
It makes hydronium.
Okay, so real quick, and I'll stop after this slide. Which protons in red is more acidic and why? This one or this one?
More acidic?
More acidic, meaning a stronger acid.
Stronger acid, I would say.
Oh, yeah, A.
Hey,
Hey,
if I
because of
pull
the
that off, I
oxygen.
delocalize it through there. If I pull this off, it's stuck
Can't
there.
delocalize it, yeah.
You can't delocalize it, absolutely.
Right.
Okay, with that being said, I'll let you guys go. I got the 15 minutes back from you guys. And there are a couple, there are about 20 slides left. 10 of them are just going over some of these concepts. But there are about 10 slides left with a couple easy concepts that I will have on the exam. Look over the next, for you, I guess it's not 10 slides, it's like probably 5 pages or whatever. Look those over. I'll go over those on Tuesday when we come back.
5
And
pages
then
exactly.
and then on Thursday is the exam. Once again, you get a full sheet of paper and everything else. During the break, if you need help, email me and I'll do the best I can to help you out with the email. Okay? Okay. Have a good break. I'll see you guys when you come back.